So we have talked about microfluidic manufacturing using silicon or glass-based systems, using PDMS-based, using injection molding and/or hot embossing. And now the last method is a new method that we're developing. It's commercially available, but it's not used by too many people, but it's gaining ground more and more. It's used in 40 labs in the world already. And it's using a polymer that we have developed that is called ostomer. And this is a novel polymer developed in our lab that is the first polymer actually specifically developed for lab on a chip. So PDMS and thermoplastics used in, so PDMS and PDMS processing and thermoplastics is used in injection molding. These materials were off-the-shelf material that somebody picked up and said, this is a cool material, maybe I can use it for microfluidics. And you can, but it has all these drawbacks, such as the main drawbacks are the poor surface control of both systems. And therefore we decided in our lab to start from scratch and make a polymer that is actually just designed for microfluidic purposes. And I'm not going to talk too much about it. It's a tile-ene epoxy, so it consists of tiles, enes and epoxies. And we mix a polymer, and the unique feature of this polymer is that in the beginning it's in liquid form, so you can pour it over a mold. You can use it also in injection molding, for example. And after you solidify it, you're going to have a material that has reactive surface groups. It's typically going to have a sulfur group and an epoxy group on the surface. So you have a solid material with reactive groups on the surface. And these reactive groups are very well controlled. So I have a perfectly controlled surface chemistry. And I can use these reactive groups for two things. One, I can use it to surface modify. So I, for example, can bind biomolecules in it. And secondly, I can use it to bond, because the epoxies are going to be able to bond. So it's a solid layer, but it's sticky. So I can take two ostomer pieces, put them together, and they will stick together like a glue. And yeah, so this is a novel material. You see some pictures of devices we made. I'm not going to talk more about it, but I wanted you to notice that there's development in this kind of direction. So let's look at some pros and cons. I understand you cannot read this very well on the video, but you have, of course, the overhead slides in PDF format. First off, lithography and PDMS. Well, it's rather inexpensive and it's fast to get started with in academia. And it's rubbery and therefore you can make pumps and valves in it, as I'm going to show in the coming slides. However, it's far too expensive for commercial manufacturing, and the surface properties and bonding properties are so bad that they are prohibitive. You know, they are not suitable for most applications. Silicon and glass-based microstructuring. You get very high quality things, very good geometric design freedom. You understand your surface chemistry is going to be glass-like. Even silicon is going to oxidize, and silicon oxide is basically a similar chemistry as glass. So you're going to have a very well-controlled surface chemistry. However, what's going to happen in reality is that these devices, microfluidic devices, are typically going to be credit card size, because very often you will have to use them in a medical setting. So your medical doctor will have a device maybe this size, and he will need to put a sample in that of some kind, or use it in a machine, so he has to be able to hold it. So it has to have a finite size with a barcode and holes for where you can put things in and out. So a device this size in silicon is going to be really, really, really expensive. You know, the small silicon chips, like even a big processor in your computers, maybe 2 by 3 centimeters or something, and then that's already very expensive. So something this size is going to be far, far too expensive actually for most applications. Yeah. And it needs to be this big because you need to be able to handle it with your hands simply. Then you have injection molding and hot embossing, which allow very inexpensive manufacturing, especially at larger quantities. However, your materials choice is limited to thermoplastics, and thermoplastics are difficult to surface modify and they're difficult to bond. Again, the cost in microfluidics is going to come from the surface modification and from the bonding. That's where most of your cost is going to be made, not from the microstructuring. And then the last material is, of course, maybe this is the future ostomer. We hope so. We think you will be able to make much cheaper devices, but with higher quality.